All right, ready to dive in. Today we're taking a deep dive into the world of mesons.
Mesons. Right.
Yeah, it all started with this essay you sent our way.
Oh, yeah.
Mesonen Schlüsselteilchen in der Quantentechnologie by, let me make sure I pronounce this right, Jorgo Schneppet. Yeah.
Yep.
It's a fascinating look at these, well, tiny particles and how they might be the key to some pretty amazing future tech.
Yeah, it seems like there's a lot of curiosity about mesons out there, what they are, how they shape the universe, what their potential is, all that good stuff.
And from what I'm getting from this essay, mesons are, well, they're these subatomic particles made up of, let me see, a quark and an antiquark, all bound together by this thing called the strong force.
Exactly. And it's that unique combo, that quark and antiquark pair, that makes them bosons, different from, say, protons and neutrons, which are baryons. And this all boils down to a property called spin.
Spin.
Yeah, spin. Mesons have a whole number spin, which has a big impact on how they, behave.
Ah, okay. I'm starting to see the bigger picture here.
Yeah.
Now, the essay also dives into these other labels, something called quantum numbers parity, charge conjugation. It seems like there's a whole system for categorizing these particles.
Oh, absolutely, yeah. There's a whole framework for understanding mesons.
But before we go too deep down that rabbit hole,
Yeah.
I'm curious, what sparked the initial interest in mesons? Where did this whole journey begin?
Well, you got to go back to the 1930s. There was this physicist, Hideki Yukawa, and he was grappling with a pretty fundamental question. What holds the nucleus of an atom together?
The nucleus.
Yeah. He knew there had to be this strong force at play, but nobody really understood what it was.
So how did Yukawa crack the code?
Well, get this. He predicted that particles like mesons had to exist to carry the strong force.
Hold on. He predicted a particle that no one had even seen.
Yep. And he even went so far as to predict its approximate mass.
That's pretty bold.
It was. But it wasn't just some random guess. Yukawa developed an equation. This equation linked the meson's mass to the range of the strong force. The heavier the meson, the shorter the distance over which the force could act.
Wow, so he was basically saying, hey, there's this particle out there, and here's how to find it.
Exactly.
So did everyone believe him? Was he instantly hailed as a visionary?
Not quite. It wasn't until 1947, more than a decade later, that a team of researchers finally found evidence of these elusive particles.
Really? So over 10 years later?
Yeah. The team was led by Cecil Powell, and they were using photographic emulsions to study cosmic rays, and that's when they found them, these particles. They call them pions, a type of meson.
Pions. Okay.
And that's when Yukawa's genius was really recognized. He even received a Nobel Prize in physics for his prediction.
Wow, a Nobel Prize. That's incredible.
It is. And with the discovery of pions, the whole significance of mesons became crystal clear. They're the glue. They bind the nucleus together.
So without mesons?
Without mesons, atoms wouldn't exist as we know them.
That's heavy. I'm starting to understand just how fundamental these tiny particles are. But the essay, it mentions that they don't stick around for very long, right?
Right. Mesons are unstable. They decay quickly through a variety of processes. It all depends on their mass and the types of interactions involved. Yeah. It's kind of like they have a limited lifespan, these particles, and depending on their individual properties, they transform into other particles.
Okay. So it's like a constant dance, this creation and destruction all happening at the subatomic level.
Precisely. And studying how these particles decay, it gives us incredible insights into the fundamental laws of physics. For example, the essay mentions a positively charged pion decaying into a muon and a neutrino. A fleeting transformation, but one that reveals, crucial information about the weak force.
The weak force.
Yeah, one of the 4 fundamental forces in the universe.
Wow, okay. So we've got mesons. They're essential for holding atoms together, and they decay in ways that help us understand fundamental forces. But are all mesons the same? I mean, they're different types of atoms, so are there different types of mesons, too?
You're absolutely right. Just like atoms come in different, structures?
Structures.
Yeah, structures. Mesons come in a variety of, we call them flavors, each with its own properties and role to play.
Flavors. Okay, I'm hooked. Let's explore this meson family tree. What are some of the, VIPs of the meson world?
All right, well, we've already met the pions, the lightest mesons, and as we discussed, key players in that strong force. But there are other fascinating characters too, like Kaons, Czech mesons, and B mesons.
Kaons, Jess, and B mesons.
Each one with a unique story to tell. So let's start with kaons. They're deeply connected to one of the biggest mysteries in physics.
Oh, and what's that?
Why there's so much more matter than antimatter in the universe.
Ah, right. The universe has a preference for matter over antimatter. But how do these kaons fit into all of that?
Well, it all comes down to this thing called CP violation. Essentially, it means the laws of physics, they behave a little differently for matter and antimatter.
So kaons, they exhibit this asymmetry.
Exactly. They give us a way to study CP violation, in a controlled setting. And that gives us clues about how this imbalance might have arisen in the early universe.
Wow. These tiny particles could help us understand the very makeup of the universe. That's mind-boggling.
Yeah, it is pretty amazing. And then you have the Mesons. Their discovery, that was a huge moment in particle physics because it confirmed the existence of something called charm quarks.
Charm quarks, that sounds, adorable.
Haha, yeah, it's a quirk of physics naming conventions. But I assure you, charm quarks are anything but fluffy. They're incredibly important to our understanding of the standard model of particle physics.
The standard model. It's like the periodic table, but for particle physics, right?
A good analogy. And Mesons, they provided crucial evidence to support that model, solidifying our understanding of the subatomic world.
So each new meson, it adds another piece to the puzzle of the universe.
Fascinating. Okay, what about those B mesons you mentioned? What makes them so special?
B mesons, they're like the heavyweights of the meson family. They contain bottom quarks, even heavier than charm quarks. And these particles, they're proving incredibly useful for studying, CP violation, but with even greater precision, pushing the boundaries of what we know about this fundamental asymmetry.
It sounds like we're constantly refining our understanding of these particles. With each new experiment, we're learning more.
That's the nature of scientific discovery. Schneppat, in his essay, he highlights how important it is not just to discover these particles, but to really study their properties in detail. He mentions spectroscopy, which involves analyzing the energy levels of mesons to determine their internal structure.
So it's like taking a fingerprint of these particles. Exactly. And through spectroscopy, scientists have confirmed the existence of even more exotic types of mesons, ones that don't quite fit the traditional mold.
You mean like those tetraquarks and pentaquarks?
Yes, the ones with 4 and 5 quarks instead of the usual 2. These exotic mesons, well, they're still shrouded in mystery, but their study could reveal even more about the strong force, how quarks interact to form these unusual bound states.
It's amazing we're still uncovering new particles, new ways that matter can arrange itself. It's like the universe keeps surprising us with its complexity.
It really does. And remember, all this complexity arises from a seemingly simple concept. Quarks and antiquarks bound together by the strong force. Schneppat really emphasizes this in his essay. It's this force mediated by particles called gluons that governs the behavior of mesons, and ultimately it shapes the structure of matter itself.
Okay, so we've got this strong force holding quarks together. But I have a question. If mesons are made of quarks and antiquarks, and, antimatter is supposed to annihilate matter, why don't mesons just, disappear in a flash of energy?
Great question. That gets to the heart of why mesons are so fascinating. See, the quark and antiquark in a meson, they're bound together in a very delicate dance. They exist in a state of, dynamic equilibrium where the forces of attraction and annihilation are balanced.
Something like a tightrope walk.
Exactly. And this precarious balance, it's what gives mesons their, fleeting existence. They're constantly on the verge of annihilation. But the strong force, it keeps them together, just long enough for us to observe them and study their properties.
That's mind-blowing. Makes me wonder if this delicate balance, this matter and antimatter interplay, could be harnessed for something practical. Could we actually use mesons for something beyond understanding the universe? For the title of Schneppat's essay, it mentions quantum technology.
You're on the right track. The essay does explore the potential of mesons, particularly in emerging quantum technologies. It's a realm where these tiny particles could have a big impact.
Okay, I'm all ears. Let's talk quantum tech. What kind of applications are we talking about?
Well, one of the most exciting prospects is using mesons in quantum computing, specifically in simulating complex quantum systems. Imagine being able to harness these particles to model the interactions of quarks and gluons, something incredibly difficult for traditional computers.
So mesons, they could be like tiny quantum computers themselves. helping us understand the universe at its most fundamental level.
That's the idea. And it goes beyond just understanding. Think about things like, well, drug discovery, material science, even financial modeling. All areas where quantum simulations could lead to breakthroughs. But we need powerful quantum computers.
Mesons could be the key.
They could be one of the keys.
Yeah.
Remember, mesons, they operate under the laws of quantum mechanics. They exhibit properties like superposition and entanglement, which are essential for building those quantum computers.
Entanglement. That's like spooky action at a distance, right? Where two particles are linked and they share the same fate no matter how far apart they are.
Exactly. And while it might sound like science fiction, entanglement is a real phenomenon. Schnephat's essay suggests that mesons, even with their short lifespans, could be ideal candidates for harnessing entanglement for these technologies.
So we could use these fleeting particles to build computers that operate on principles that still seem, well, kind of like magic.
It's a testament to the power of exploration. What was once just theory is now being investigated for practical applications. And Schnephat, he even mentions specific experiments already underway, exploring the potential of mesons in quantum computing and other quantum technologies.
So quantum computing is one application. What else is out there?
Another fascinating area is quantum sensing. Imagine using mesons to create ultra-sensitive detectors. Detectors that can measure things like, gravity, but with unprecedented precision.
Gravity. That's one of the fundamental forces of the universe.
Yeah.
Why would we need mesons to measure it?
Our current understanding of gravity, it's incomplete. It doesn't quite mesh with our understanding of quantum mechanics. And mesons, with their unique sensitivity to fundamental forces, they could provide new insights into gravity's nature.
So they could be like, what, tiny gravitational probes?
Exactly. And it goes beyond gravity. Meson-based sensors could have applications in, well, medicine, navigation, even in the search for dark matter.
The potential seems vast. It feels like we're only scratching the surface of what these particles can do.
And that's what's so exciting about it. There's still so much we don't know, and each new discovery opens up more avenues to explore. It's like we're on the verge of a new era in quantum technology, and mesons, they might just be one of the keys.
All this from particles that exist for, what, a fraction of a second? Remarkable.
It is remarkable, and it reminds us that even the smallest, most fleeting things can have profound implications, not just for our understanding of the universe, but also for our ability to shape the future.
Schnephat's essay has definitely given us a lot to think about. We've gone from the building blocks of matter to the future of quantum technology, all thanks to these fascinating particles.
It's a testament to how interconnected everything is. Schnephat does a great job of highlighting how something seemingly insignificant can have profound implications.
And it makes you wonder, what other mysteries are out there? What other particles or phenomena might be holding the key to unlocking even bigger secrets of the universe?
That's the question that keeps scientists going, and it's what makes this field so exciting. There's this constant exploration, this drive to push the boundaries of what we know.
It's like we're explorers, charting a new frontier. Each new discovery expands the map, revealing even more uncharted territory.
A perfect analogy. And it's not just about knowledge, it's about the potential for these discoveries to lead to new technologies, new ways of interacting with the world.
Speaking of technology, I'm still thinking about those potential applications of mesons. Quantum computing, quantum sensing. It's mind-boggling to think that something so small could have such a large impact.
It is, and it really highlights the importance of investing in fundamental research. We often don't know where these explorations will lead, but history shows that breakthroughs in basic science, they can have profound and sometimes unexpected consequences for technology and society.
It's like planting seeds. You never know which ones will grow into those towering trees, but you have to keep planting to ensure a vibrant and thriving ecosystem of knowledge.
A beautiful analogy. I think Schnephat's essay does a great job of planting those seeds for us.
Yeah.
It sparks curiosity, challenges assumptions, invites us to think differently about the universe.
That's what the deep dive's all about, right? Exploring new ideas, delving into these complex topics, and emerging with a deeper understanding of the world around us.
Absolutely. So to our listener, keep exploring, keep asking those questions, keep diving deep. Who knows what amazing discoveries await?
A big thank you to Yurigo Schnephat for providing the inspiration for this deep dive into the world of mesons. His essay has given us a glimpse into a fascinating and ever-evolving field and its potential to shape the future. Until next time. It's amazing to think about how much we've learned about the universe just by studying these tiny particles.
It really is.
It makes you wonder what other mysteries are still out there. What other, I don't know, particles or phenomena might hold the key to even bigger secrets?
Well, that's the question that keeps scientists going, right? It's what makes it so exciting.
Yeah, it does. There's so much we don't know.
Exactly. And that's what drives the exploration, this drive to push the boundaries to see what's out there.
That's like we're explorers, charting a new frontier. With each discovery, the map just keeps getting bigger.
A perfect analogy.
And it's not just about knowledge for knowledge's sake, right?
Mm-hmm.
It's also about the potential to create something new. New technologies, new ways of interacting with the world around us.
Yeah, absolutely.
Speaking of technology, I'm still thinking about those potential applications for mesons. Quantum computing, quantum sensing. It's mind-boggling that something so small could have such a huge impact.
It is. And it highlights why investing in fundamental research is so important. We don't always know where those explorations will lead, but history's shown us time and time again that these breakthroughs, they can have consequences. Profound consequences, really. For technology, for society, even in unexpected ways.
It's like planting seeds. You might not know which ones will grow into those massive trees, but you have to keep planting. If you want a healthy ecosystem, you've got to keep nurturing that growth.
Beautiful analogy. And I think Schneppat's essay, it does a great job of planting those seeds for us. It sparks curiosity. It makes you question things, your assumptions. And it invites us to look at the universe in new ways.
And that's what the deep dive is all about, right?
Yeah.
Exploring new ideas, diving into these complex topics, coming out the other side with a deeper understanding, a new appreciation for the world.
Well said.
So to our listener, keep exploring, keep asking questions. Keep diving deep. You never know what incredible things you might discover.
Couldn't have said it better myself.
A big thank you to Jorgo Schneppet for the inspiration for this deep dive into mesons. His essay gave us a glimpse into a fascinating field and, well, its potential to shape the future. Until next time.